In this video, we're going to try to take a look at example number 2 to see how using these blue and red identities actually works in a new scenario, and then try to see if we can summarize some of the things that we've learned in the box that you can see on the bottom of the page here. So here you can see we have a sine of x to the 4th power. And this seems to have a lot of what we would need to use either the red Pythagorean identities or those blue ones, which were the double angle formulas. Now, interestingly here, I can see that if I was to go ahead and maybe pull something off to the side to save as like a du portion, I could maybe imagine saving something like this, right? Because I have a sine that I can pull off of this stack of sines. But if I was to go ahead and do this, I can see then that I'm going to have to deal with a sine to the 3rd power. And if this here is operating as my du, then my u would have to be something like a cosine of x. So its derivative would be something like a sine. But what that presents as a dilemma is that I'm going to still have an odd number of sines here, and that's kind of tricky to use the identities up above to replace, because all the identities up above really had sines raised to the 2nd power. So with this in mind, I might be able to see that, again, a red identity here might be difficult to do because it doesn't seem like I can force a u substitution to happen in the way that I would want. Therefore, instead, what I'm going to do is think about rewriting my integral in the following way. I think I can rewrite this as a sine squared of x times another sine squared of x. And I'm going to attempt to go ahead and use some blue identities to make these replacements. So in place of the first sine squared, I can put a 1/2 1 minus a cosine 2x, and I can do the exact same thing for my other for my other sine squared. Now, of course, once I have this, this looks just like a gigantic mess. I can simplify it down maybe a little bit, right? I can express this as a 1/4 times this 1 minus cosine of 2x, I guess, squared. But how does that really help? Well, this is why at the very first video I said that it was probably going to be the case that we would often have to use algebra mixed in with these trig identities to help us simplify down some stuff that we're working with. In this case, notice since I have a quantity squared, it may be advantageous to go ahead and to say, why don't we multiply that quantity out? So I'm going to go ahead here and take my 1/4 out to the front of the integral, and then multiply out the rest of this quantity. So that would get me 1 minus 2 cosines of 2x, and then plus a cosine squared of 2x. Now, I can start to see if I can begin to do antiderivatives pretty easily. Very clearly, I can take my 1 and transform that into an x. This piece here is actually pretty simple. You think about what you would take the derivative of to get 2 cosines of 2x? Well, you actually could just do sine of 2x. I get cosine of 2x, and the chain rule would give me exactly the 2. But over here, this is where I get something a little bit more difficult, right? What do I do with that cosine squared? Oh, well, based on what we talked about in the last video, using another blue identity here might make this a whole lot easier to work with. So I'm going to go ahead and actually use another blue identity on this portion. So let's go ahead and write out what this would look like. I'm going to have a quarter. I still have my 1 minus my 2 cosine of 2x. And then I can replace that blue stuff with another 1/2 1 plus cosine. And remember that the angle that occurs in here is always double the size of the angle from here. Just like at the start, I had a sine of x, and so that angle got doubled to be double x. But here, if I already have 2x, when I double, I should get 4x. It's twice as large. So now I have this. And while this may seem a bit more complicated at first, if I simplify it down substantially, I'll see that it's actually going to be really easy to integrate now. Notice that here, if I distribute my 1/2, I'm going to get a half and a 1 in front, which I'm just going to go ahead and write as 3/2. I still have my minus 2 cosine of 2x, and I'm also going to have a plus a half cosine of 4x. I think each of these now is going to be fairly easy to do an antiderivative of. Here's what we're going to get. Obviously, I'm going to have 3/2 x. We already saw that we could have sine of 2x to generate that middle term, but what about the back? What can I take the derivative of that would leave me with a cosine of 4x, and then also times a half? Well, again, you can slowly start to workshop this. I could say, how about I do sine of 4x, because I know its derivative at least is close to this. Derivative of sine of 4x is going to be cosine of 4x, but times a 4. And I don't want a times 4, I want a times a half. So what could I put in the front so that times 4 combines with this other thing and leaves me with just a 1/2? Well, you could see that I could choose something like a 1/8. And then, of course, at the back, I can put a plus c. And so this leaves me with a nice, easy answer that I can see was generated only from using these blue identities. And so we can kind of see that there's a general theme here. When I have trig functions that are raised to even powers that can be separated out into sine squareds or cosine squareds, using those blue identities is pretty nice. And if I have an odd number of sines or cosines, there's a good chance I can start to go ahead and actually use those red identities to force a u substitution. Now I'm going to go ahead and try to summarize what we found here in this box below. I think it's really important, though, that we don't just memorize this box. Purely memorizing and attempting to just memorize blind patterns is one of the worst things you can do in a math course. It may have very good short-term benefits, but in the long run, you're actually going to cripple yourself. You're not going to be able to perform very basic tasks because you haven't been able to train your mind to understand what you're looking for. Instead, you're just trying to recognize patterns and not really thinking through what's going on. So as I summarize these things down here, don't treat this as stuff to memorize, but maybe as something to help jog your memory as you review this material at a later time. So let's start with thinking about strategies then for evaluating sines and cosines in the same integral, but maybe raised to different powers. So let's start with this. How about we start with what happens if n, that's the power on the cosine, is actually odd? Now we saw something like this actually all the way back in our general idea. When I have that odd power on the cosine, I can immediately start to think about saving a cosine to use as a du and changing everything else into sines, so I'm ready to do a u substitution. So I'm going to go ahead and try to summarize that. If n is odd, I'm going to save a factor of cosine of x to be a part of du. I'm then going to replace all remaining cosines using our nice identity, sine squared of x plus cosine squared of x is equal to 1. And then we were able to perform a u substitution. Specifically, we did a u sub where u was going to be equal to the sine of x, and du was going to be equal to cosine of x dx. Remember, that's why we saved that factor of cosine. Now you could imagine the same sort of thing being done if I had maybe had a problem with like sine to the third power. So if I end up with m is odd, then I can almost do the exact same thing. I would start by saving a factor of sine of x, that's again, so it can be a part of the du, I can then replace all remaining sine of x using, again, our nice identity of that sine squared plus cosine squared. Oops. That's going to look like not equals, so let me adjust that. Equaling 1. And then I could go ahead and perform a u sub. This time, though, notice that if my du is supposed to contain my sine of x, my u has to contain cosine of x. Notice then down here I'm going to have a negative sine of x, but of course we know that that's actually perfectly okay. I can just move that negative to the other side. So it's kind of in these cases where I have some odd powers that I end up really seeing that these red identities work really well, and I try to force out a u substitution. However, in the last two questions, that is, in example number 2, we had an even power. In example number 1, we had an even power, and those were times where I used those blue identities, those double angle formulas. Notice here then, I'll state that if m and n are both even, I can go ahead and just say that I should use double angle identities, which again, remember, are those blue ones. So if these are both even, I'll tend to use those blue identities. Notice that if one was even and one was odd, I can kind of just use scenario 1 or 2 here. And if both m and n were odd, I guess I could kind of choose whether I want to do a u sub where I save a cosine or a u sub where I save a sine. The choice would really be yours. Now I'm going to go ahead and suggest that you, again, don't memorize the box. You can use it to review, but don't just blindly memorize what's going on. Try to see if you can really understand how we're using this idea. And a great way to try to practice that is to take a look here at example number 3. This is one that I'm not going to go over in a video, but I would encourage you to go through and try it. And of course, you can check the solution up in Blackboard.